Hi everyone, right, so video 2, second attempt after the sound messed up. Now, let's just recap where we are. So last time we talked about logs. What were logs? Well, we had index form, which said a to the b equals c. So index form says, give me a base, give me a power, and I'll tell you what the result is. Log form said, well, no, actually, if you give me the base and the result, I'll tell you what the power was. Okay, so it's log is the inverse of the index form. So when I say index form, I mean an exponential graph. So y equals 10 to the x, or y equals 2 to the x, or y equals 3 to the x, yeah? And they all had a asymptote at y equals 0. If I whack in x is 0, I always get 0, 1, don't I? And there we go. There's my y equals 2 to the x graph, say. But what does the log graph look like? Well, the log graph is a mirror image of that in the line y equals x. So if I drew y equals x, everything is reflected. So not having an asymptote at y equals 0 anymore, I have one at x is 0. I don't cross at 0, 1 anymore, I cross at 1, 0. And I go to infinity like so. So this is your y equals log base 2x graph. Okay, there we go. There's our graphs. We use logs to bring powers down and find what the power is. Okay, so the graphs are really important. You're going to be transforming those, and also what you're about to do is really important. Now there are 6 laws for logs, and they all follow the precepts of indices laws, because logs are based on powers, aren't they? So what are the log rules? First two, easy to remember. So if I have log A1, what does that mean? What is log A1 always going to be the same as? So if I had log 10(1) or log 7(1), what's that always going to be the same as? Well, log A1, let's call that Z. And if we put that in index form, we get a to the result is the power. What must z be then? If a is any number, in order to get a to the power to be 1, my power must be 0, mustn't it? A to the 0 is 1, a million to the power 0 is 1. So log A1 is always 0. Alright? Important property. Log AA, what's that going to be the same as? So let's do it again. Log AA equals Z. So base, power, result. A to the Z must equal A to the 1. Base is the same, so therefore powers are the same. So Z must be 1. So log AA must be 1 because A has been raised to the power of 1 to get the result of A. So there you go, and 2 important results there. Okay? Second important, other important results is that A must always be positive. The base here must always be positive. Think about it, it's the inverse. That's why it's so important. That's why you won't understand if you don't realize that the base must be positive because your base for the exponential is positive. Okay, so log is only defined for positive bases because it's the inverse of exponentials. Likewise, this element here, so what if you had log 2x, x must always be greater than 0, mustn't it? Why? Because you know it's got an asymptote. You know the graph has an asymptote at x equals 0. You know x can't be negative. Okay? So there are important properties here. So if log 2x, x must be positive, and the base must be positive. So these are important things that you need to be aware of, and that should answer why can't these things be negative, because think about what log is in terms of the inverse of the exponential. Other laws. So these we're going to prove in class, but I'll prove one with you. So log AB plus log AC is always the same as log A, B, C. So the results times each other, right? It only works if the base is the same. So the base must be the same in order for this property to work. You're going to need all these laws to solve problems, okay? And we're going to prove this in a minute, and then you can prove the rest in class. Likewise, if we minus them, subtract them, this will be the results divided by each other in the brackets, okay? If we have log a b all to the power of n, so it's just b to the n, not log a b to the n, just the b is raised to the power, then the n can come down. So this is your fifth law. You must know all these laws. So stop the tape, write them out, memorize them. You must remember this stuff because we're going to be using it all the time. The last one is changing base. Now, like I said before, you got that magic calculator at the moment with that magic button, log a, you can put in the value there and you can put in the value there. Now, traditionally, we only had on the calculators log, which as we said in the earlier video, that means log base 10. So on your calculator, you can see a button which says log, which is log base 10. But before that, people had to look up tables, paper tables, to give you results because someone had worked it all out in advance using that Maclaurin series. Like I said, the calculator just draws off what's called a Maclaurin series. That's how it comes up with the results. So, when we had that log button though on our calculator, and we had problems like log 2x and log 3x and stuff, we have to convert it to base 10 so then we can use our calculators to get a result. You guys don't have to do that because of the magic button, but you will have to do it because they'll make you do it in terms of algebra problems. So it's important to know how to change a base. So if we start off with log base a b, if I want to change it to log base c, my rule is log c old result, log c old base. Okay, so log cb over log ca. Really important that you know these formulas. So log new base old result, log new base old base. Okay, so if I wanted to change, for example, in that sixth rule, 7x, and I wanted to change it to log base 10, I'd have log 10 result, log 10 old base. You see? That's how I could change my base. Let's do a proof then on how, because you don't want to just take rules. So let's actually prove where one of them comes from. So I want to prove that log AB plus log AC is the same as log ABC. And if I do this for you, you can definitely do log AB minus log AC is log ABC. So how I would prove it, so this is a proof. You don't have to know this. This is just for your understanding. But I do think it's important that you understand where things come from in order for you to make connections. It just makes you much more mathematically aware, let's say. So let's say we let x be log AB, and I'll also let y be log AC. So at the moment, if I do x, if I put this, because at the moment this is in index form, this is in log form, sorry. So if I put it in index form, I get x is my base, sorry, a is my base, x is my power, and b is my result. Likewise here, a is my base, y is my power, c is my result. So if I times the two together, so a to the x times a to the y, I get bc. Hopefully you're starting to see where this is going. And you know that when you times two things together with the same base, their indices plus. So we're here. Now if I put this back into log form though, so log base A, result is BC, equals the power. But what is x and y? X is log AB, which is what we started with, and y is log AC. And it's finished. Proved. And while we're here, we might as well prove one of the other ones as well. Why not? Why not? How about we prove number 5? How about if we do the log AB to the n one? And this will show you how proofs can just kind of domino affect each other. So let's prove this one. We'll prove that this is the same as n log AB. Well, if we start on the left-hand side, so LHS, log AB to the n is the same as log A, and remember what B to the n is. That's B times B times B times B times B, right? And we know, well, how many B times B times B times B is that? We know that's n times, don't we? We just did a proof that said when you plus logs together, it's the same as the results times each other. So this is the same as log AB plus log AB plus log AB n times, isn't it? There are n lots of log AB. And there you go. It's proved as required. You see? Number 5 is pretty easy once you've done the other one. Let's do a couple of solves then. How can we actually use this then to solve equations? So here's my equation. I want to try and find out what x is, and I'm going to use my rules in order to do it. So I can see there's a minus here. So hopefully you're thinking, well, I need to subtract them. Hopefully you're thinking I need to go, well, log AB subtract log AC is the same as log A B over C. But I can't use that yet because of the 2. You see? So now I need to use the 5th rule first. So log 10 x to the power of 2. The 2 comes over the x, not over the whole thing. It is not log 10x all squared. It's just log 10 x squared minus log 10 7 is log 10 63. Now you can use that rule above because the log's by itself. So x squared divided by 7 is log 10 63. Log 10 is the same. Log 10 is the same. So therefore x squared over 7 must equal 63. So x squared is 63 times 7. So 63 times 7, 441, and therefore x is the square root of answer, which is plus or minus 21. But is it? Can x be plus or minus 21? No. No, it can't. X can only be 21, can't it? Because x must be greater than 0 in order for this to work. We know the asymptote is at x equals 0 and no negative numbers, so it must be 21. Okay, big note to yourself. And whoops, last example then. So let's solve this one. We can't do anything with this yet. Can't use any other rules because our bases aren't the same. So we need to change our base. So we need to know our change the base rule in order to solve this problem. So log AB is log CB log CA. So this one's by itself, therefore it's the easiest. I'm going to change it to be base x. So log 2x is the same as log base x, new old result, log x 2, old base, yeah? So log x, old base. What is log x x? We just talked about that. So let's see where we are. So log 2x, we just found out, is log xx over log x2 equals 8 plus 9 log x2. Log xx is 1, isn't it? Over log x2. 8 plus 9 log x2. Now, what do? We're trying to get log x2, so we're going to times everything by log x2, aren't we? So we're timesing up log x2 plus 9 log x2 all squared. Okay, so I've times everything by log x2. And remember, that power does not come down because it's not 2 squared, it's log x2 all squared. So hopefully you're screaming out at the video and going, it's a quadratic. Because it is a quadratic in a sense, isn't it? If I let y be log x2, then you can totally see it as a quadratic. So 9y squared plus 8y minus 1 is 0. Now you can factorize this thing, and we'll solve for y. So you don't have to do the y thing, but some people like to do it because it helps them out. So y must equal a ninth, y must equal minus 1, but we didn't start with y, so we can't finish with y. So log x2 is a ninth, log x2 is minus 1. So you've got to go back to index form now. So base x to the ninth is 2. Base x to the minus 1 is 2. So that is x to the minus 1 is 2, so that's 1 over x is 2, therefore x must equal a half. Here, we need to make x the subject, so that's x to the ninth. If I raise that to the power of 9, that will get rid of that ninth. So x is 2 to the 9, which is 2 to the 9, it's been a long day, 512. Whoops, so 512. And there we go. We're finished. You could sub that back in if you want into your calculator to check those values.